So in other words, if solubility is the maximum concentration, it is the concentration of a saturated solution. So we are going to be looking at questions where we are given the solubility. So we'll be given a concentration, and we will be asked to find the KSP. And you will get marks as follows. You get a half a mark for writing the solubility equilibrium equation. You get a half a mark for writing the KSP expression. Now, ion concentrations, if it's really simple, if it's like a 1-to-1 ratio, it's probably going to be like 0.5 marks. If you have to go from grams per liter to moles per liter and like find a 2-to-1 ratio, maybe it's worth 2 marks, okay? But basically you are finding the ion concentrations in moles per liter. And these are all going to be dump and stir type problems, which means there's only going to be one compound. And what will you do with that one compound? You will dump it into the water and you will stir it. And if you dump the one compound into the water, let's say you had A2B, what can you say about the concentrations of A and B if we just dump A2B into solution and stir it? The concentrations are 2 to 1. Okay, so that's the kind of problem we're going to have here, because we're going to give you the concentration of A2B, okay? And then we're going to say, oh, what's the concentration of A? What's the concentration of B? So in other words, the ion concentrations are proportional to the coefficients. And then once you've got your ion concentrations, you're going to plug them into the KSP and solve. And that is worth between half and 1 mark. Now, option or steps 1, 2, and 3, you can do in any order that you want to. Doesn't matter if you find the ion concentrations first, or if you write the solubility equilibrium expression first. Whatever you like. Let's take a look at example 1. The solubility of barium sulfate is found to be 1.05 times 10 to the minus 5 molar at 25 degrees Celsius. And we want to calculate the KSP. So the first thing we want to figure out is, how can you tell that this is a dump and stir type problem? We just have one compound. Do you guys think you could try this question on your own using those steps at the top of the page? Give it a try. If you finish, you can move on to example number 2 on the next page, okay?
No, we finished it all yesterday. Okay, so I would like. You feel good about the content? There's one question that we have on like and I feel like if I look on Friday, we just mark it. It's just like that. Yes, don't have to do a race to you can just skip sort of the whole race part and you just say this is 1 to 100. No, I would just get rid of this and I would just be like, okay, it's 1 to 1. Yeah. Okay. Okay, so you have this here. And this one. So what's the concentration of that? Okay, I do the same because it's one and that was also going to be the same because they're all one. Yeah.
I want you all to check your solubility equilibrium equation and make sure that you have an equilibrium arrow. Okay? Now, because this is a 1-to-1-to-1 relationship, you don't actually need to show the work for finding the ion concentrations. But if you wanted to, and if you're confused, if you're like, how do I find those ion concentrations? We know that the concentration of barium sulfate is 1.05, sorry, times 10 to the minus 5 molar. And because these are all 1-to-1 to 1, then barium will also be 1.05 times 10 to the minus 5 molar, and sulfate will also be 1.05 times 10 to the minus 5 molar. If you didn't write this part, because it is 1 to 1, it would be okay. You could just go ahead and say, I know that barium sulfate is 1.0 times 10 to the negative 5. Therefore, both of these guys are 1.05 times 10 to the minus 5. And then I would have to square it. And you get 1.10 times 10 to the negative 10. So you have your solubility equilibrium equation. You have your ion concentrations. You have your KSP expression. You plug in your values and you get your answer. Shall we try the one on the next page? Okay. A saturated solution of silver bromide contains 1.33 times 10 to the negative 4 grams per liter. Is this mix and match or is this dump and stir? Dump and stir, just one compound, okay? So everything's going to be proportional. We're going to have 1 to 1 to 1 in this case. You'll notice, though, that what do we have here? Grams per liter. Can we do a KSP using grams per liter? No. So we need to first convert that to moles per liter, and then you can go from there. Do you guys want to give that one a try? Okay. And like I said, if you finish example 2, you can move on to example 3. If you finish example 3, you can start on the exercises. I think I assigned exercise 1 and 4, I think. Oh, it's bromide. Silly me. Did you guys get 7.08 times 10 to the negative 7 moles per liter? Excellent. By the way, this SEE thing, no one other than me calls it that, I don't think. So if you go off to university and you're like, I'm going to label my SEE and they'll be so happy with me, they probably won't know what you're talking about. However, if you want to label it so you remember to do it, that is perfectly good. Did you get 5.02 times 10 to the negative 13? Hooray! That means you're ready for example number 3, which adds one more layer of complication because we have a little 2 there. Okay, so that'll require a little bit of thinking about on your part. Give it a try. Yeah.
Can I find out the moles of
Yes.
1 to 1? So it's this.
Yeah.
And then which equals to the 2OH minus.
Yes.
And then, okay. So we can do molarity and moles for this 1 to 1 ratio. And
Yes.
only molarities and moles.
Yes. Yes. Well, which one would it be? Is sulfur going to be? Yeah, because otherwise we would have to divide this by two. Spend time over here, right? No, you're right. Yeah, you have to start. Yeah. Now watch out, because you're going to doing. What is that times two for? You know what I mean? Like, there's just like some gaps in the work there. Yeah. Oh, it's wrapping up. I'm finished. Oh, see them. There you go. No problem.
Oh, I didn't know this, but
Yeah, you can see the equals. Sorry. Because I'm horribly scared.
what? I am not getting.
Now.
Mine's also 10 names.
Oh, also. We need a line of concentration. This for one. Yes. So that concentration is twice as. Oh, yes.
Yes, yes.
Yes.
Yeah.
Yes.
Yes.
Okay, I got really excited with my highlighting in the other block because I'm like, these are all the things you have to do to get marks. So let me just do a little erasing of all my highlighting. And I don't know why I rounded off in here. I think it was just because I was too lazy to write out all the digits when I was showing my concentrations, but I wrote out all my digits down here, so. Huh? You might not. You probably don't. I get a little excited about it because every once in a while when I don't keep 2 extra digits, it's wrong. You don't have to write it anyway. You can just keep it in your calculator. Do you know what I mean? Yeah. I have an old-fashioned calculator that if you press all clear, it's just all gone all the time. So, and if you mess something up, you just have to start from scratch. So I tend to write things down.
I don't think it's necessary for calculus, bro.
Oh, for calculus, I'm sure they don't care.
Oh, no, they do.
Oh, they do care. Oh. They probably want you to write things as root 2 times whatever and things like that.
Oh, that just was, oh, absolutely, throw myself off it.
And then because that got taught in calculus, I got or pre-cal or whatever. Anyway, everybody started giving me chemistry in like 4/3 root 2, and I'm like, oh, give me a decimal, man. Just like, what is that nonsense?
Yeah, we're trying to keep it at a whole number.
Yeah.
Because of chemistry, I started writing my negatives a number and then minus instead of minus and a number. I caught myself doing the on test like twice already.
You're so fucking smart.
So is this example, does anyone have questions about this? Are we feeling pretty good? Excellent. So that means that you're going to be ready to do the exercises from this section when you go home. But today we are going to move on and take a look at page 60. Does a precipitate form? And we're going to hang out with Mr. Colger. And there's all sorts of fill in the blanky kind of stuff here, so you can follow along with it. Okay. And we are going to go here. And I want to go to WCLN does a precipitate form. Yeah. Sorry, it's just too loud. And then he talks and
We'll
it's not
show
as
you
loud.
how to predict whether a precipitate will form when 2 solutions with given concentrations and volumes are mixed. We'll do this by going through an example. We're given that 500 milliliters of 2 times 10 to the negative third molar PbNO3 is added to 300 milliliters of 0.11 molar KBr, and we're asked to use calculations to determine whether a precipitate will form.
Sorry, I don't want to give away the show too soon. Okay, there we go. That's going to send all you OCD people like crazy. I'm sorry, I will finish erasing it.
Beakers with these 2 solutions and the ions they contain are shown here. The left beaker contains 500 milliliters of 2 times 10 to the negative third molar PbNO3 and the right beaker contains 300 milliliters of 0.11 molar KBr. The lead 2 nitrate solution is poured into a larger beaker, like this, and the KBr solution is poured on top of it, like this. Then they are mixed. The final mixture contains all 4 ions, Pb2+, NO3-, K+, and Br-.
Okay, so my first question to you is, this is eventually going to involve a solubility equilibrium equation. Okay. Who are we writing the solubility equilibrium equation for? What compound? So don't say it out loud, but chat with your neighbor, like say it quietly with your neighbor. What compound will we be writing the C for? Solubility equilibrium equation. Discuss. So you've got 4 choices. For which of those will you write the C? Chat with your neighbor. We're going to vote. Okay?
That's what I'm saying. Why do you I'm also
All right.
stop.
Here's how you show the letter A. You put your fingers on your palm and you put your thumb beside your fingers. That's an A. Yes. And then B, you put your palm flat and you put your thumb on your palm. So that's a B. And then C is just C. And then D, you put your pointer finger up and the rest of your fingers form a circle. So pointer finger up and the rest of your fingers form a circle. So you get to choose either, do them all with me. Here's A. Here's B. Here's C. And here's D. Okay? So you get to choose A, B, C, or D. Are you ready to vote? 5, 4, 3, 2, go! I got some A's, some B's, some C's. Okay. What do we know about all nitrate salts?
They are soluble.
They are all soluble, so this will be aqueous. What do we know about all alkali metal salts? They're all aqueous. What do we know about all alkali metals and all nitrates? They're aqueous. And what do we know about lead bromide if we consult our chart? It is not soluble. What kind of compound would we write a solubility equilibrium equation for? A soluble compound or a low solubility compound? Low solubility. So you would need to say who's going to be the solid, and then you'll write the solubility equilibrium equation for the solid. All right? So that's the first thing. The second thing is we are going to need some ion concentrations, yes? Now, what did we just do when we mixed these two things together? What did we do to each of them? We diluted them. Could you find the diluted concentration of lead nitrate, please? I'll write out the information up here in case you're having problems seeing it. So you guys know how to do dilution calculations, right? Because you reviewed it.
Yes.
And if you didn't review it, shame on you. Not shame on you. Just try and find some time to do that in the next little bit because they're obviously you're going to have to do them. Can you do it? Try. I want you to find the concentration of PbNO3 diluted. Okay? And if you need extra paper, you can find yourself some extra paper. Yes, that is wrong. It's totally possible. Yes, that's number 4. 7, 9. Yes. Here, have some extra paper so you've got room. I just want you to do that calculation. Yeah. So you're finding the diluted concentration of the lead matrix. Okay. Anybody else need some paper? You're squawking in, are you? Like some paper? Okay. Anyone want some paper? You're good? I just want stuff.
Yeah, that's what I have.
Yeah, but I mean, one.
Yeah, which is that? That is
That's what fun is. How much is it?
Mm-hmm. You can't just look at your paper.
All the numbers are there.
Well, it doesn't because we're not concerned about the KVR.
Okay, so
Do we care about the KBR right now?
No.
No, the KBR is just floating around, minding its own business. For now, you can just ignore this because you are focused on the lead nitrate.
Oh.
Okay. Right.
What's our V2?
800
800 milliliters because we're putting the two volumes
Together.
together. I really like this version of the dilution formula. In fact, I always just call it the noon equation when I write it in this format. Because what you've got is you've got your new concentration is equal to your old concentration times the old volume over the new volume. Now, you don't need to remember that if you don't want to. You can simply use M1V1 equals M2V2. But if you are diluting something and you want to find the new concentration, you can use the new formula. And it will give you a dilution factor. Do you see how this is a 5/8 fraction? Yes? We have diluted this thing by 5/8. Yes? 5 parts in 8. Yeah? So numerically, this always kind of made a little bit of sense to me because it shows me the actual fraction that I have of my original concentration, which I like. Okay, but if that makes no sense to you because you're like, I don't see that, then just solve M1V1 equals M2V2 and be happy with that. Okay? And what do we get when we solve this? 1.3 times 10 to the negative 6? That can't be. Negative 3 molar? Okay.
Oh, I think
Could you tell me then, that's the concentration of lead nitrate. What is the concentration of lead? It's the same because lead nitrate contains how many leads? 1 lead. What would the concentration of nitrate be? We don't care in this question, but what would the concentration of nitrate be? Twice that much because there's 2 nitrates. Okay? Would you be able to use the same method to find the new concentration of the KBR? Can you do that? Find concentration of KBR? So I could actually put this over here and I could say my concentration of lead is equal to lead nitrate. Yeah? Do you guys need another minute or are you good? Okay, so I'm going to let Mr. Colger show us.
And the final volume of the mixture is 500 milliliters plus 300 milliliters, which is a total of 800 milliliters. Possible combinations of ions in the products could be Pb2 plus and Br minus, which could form PbBr2, or K plus and NO3 minus, which could form KNO3. K plus and NO3 minus are both spectator ions, so KNO3 will not be a precipitate. Therefore, we can discard these ions from our diagram. According to the solubility table, lead-2 bromide is classified as having low solubility, so it could form a precipitate if the concentrations of the lead-2 and bromide ions are high enough.
So anytime you have a mix and match, you need to figure out who is the solid that we make. Yes? All right.
In order to find out whether a Pb2 plus and Br minus form a precipitate or not, we need to determine what is called a Ktrial KSP for PbBr2.
This is also known as a Q or or Ktrial. Okay? It's got many, many names.
The Ktrial KSP is sometimes called Ktrial, experimental ion product, or simply ion product.
Now, what happens if our Ktrial KSP, we plug in our ion concentrations and we get a value bigger than KSP? That means our ion concentrations are too big. And if the ion concentrations are too big, will we get a precipitate or not?
No.
If your concentrations are too big, that means there's not enough room at the hotel for everybody. So what will happen? Precipitate, right? Now, what if you have your ion concentrations, you multiply them together, and you get a value smaller than KSP? That means that there's not enough ions to fill the hotel, right? Too small. So will we get a precipitate? No.
Here we'll call it the Ktrial KSP. The Ktrial KSP of PbBr2 is calculated by finding the concentrations of Pb2 plus and Br minus in the new mixture, and inserting these into the KSP expression for PbBr2. It is called Ktrial because these concentrations are not at equilibrium. Here's how it works. If the Ktrial KSP is smaller than the actual KSP for PbBr2, then no precipitate will form. But if the Ktrial KSP is greater than the actual KSP, then a precipitate will form.
So if you're filling in along with us, there's blanks there that you can fill in. I don't know what page it's on. What page are we on? 61? Yeah, okay. So if Ktrial KSP is too small, no precipitate. If it's too big, then precipitate.
In order to calculate the trial KSP, we need to find the concentrations of Pb2 plus and Br minus in the new mixture. The source of Pb2 plus ions was the 500 milliliters of 2 times 10 to the negative third molar PbNO3 When it was mixed with the other solution, the PbNO3 solution was diluted from 500 milliliters to 800 milliliters. Because PbNO3 contains one Pb2 plus ion, the initial concentration of Pb2 plus before mixing, which we'll call C1, is the same as the initial concentration of PbNO3 before mixing, which is 2 times 10 to the negative third molar.
So he's just going to walk you through this calculation again. So if you're feeling like you just want a little review of it, it's here. He calls M1, instead of saying molarity 1, he's saying C1 for concentration 1. It's the same formula though. Okay, C1 is the same as M1.
Which we'll make a note of up here. In order to calculate the concentration of Pb2 plus in the mixture, we used the dilution formula. C1V1 is equal to C2V2, where C1 and V1 are initial concentration and volume, and C2 and V2 are the final concentration and volume. Solving for the final concentration, C2, we get C2 equals C1 times V1 over V2. The ratio V1 over V2 is called the dilution factor. The dilution factor is always the initial volume, V1, over the final volume or total volume, V2. So to find the final concentration, C2, of an ion after mixing two solutions, we take the initial concentration, C1, and multiply it by the dilution factor, V1 over V2, or the initial volume over the final or total volume. So the concentration of Pb2 plus in the new mixture, which we'll call the concentration of Pb2 plus final, is the concentration of Pb2 plus in the original PbNO3 solution, or concentration of Pb2 plus initial, times V1, or initial volume, over V2, or final, or total volume. The initial concentration of Pb2 plus in the original PbNO3 solution was 2 times 10 to the negative third molar. The initial volume of the PbNO3 solution was 500 milliliters. And the final, or total volume of the new mixture is 800 milliliters. The milliliters will cancel out. We take 2 times 10 to the negative 3 molar and multiply it by 500 over 800, and the answer is the concentration of Pb2 plus in the new mixture is 0.00125 molar. And we'll make a note of that up here. Now we'll calculate the concentration of bromide in the new solution, or the concentration Br minus final. Since Kbr contains one Br minus ion, the concentration of the bromide ion, Br minus, is the same as the concentration of the original 0.11 molar potassium bromide solution. We multiply the initial concentration by the dilution factor, which is the initial volume V1 over the final volume of the new solution V2. The concentration of Br minus in the original Kbr solution, or concentration Br minus initial, is 0.11 molar. The initial volume of the original Kbr solution V1 was 300 milliliters. And the final volume V2 is the total volume of the new mixture, 800 milliliters. Again, the milliliters can be cancelled out, and 0.11 times 300 over 800 is equal to 0.04125 molar. We'll leave this unrounded until the end of the calculations. And we'll make a note up here that 0.04125 molar is the concentration of Br minus in the new mixture. In order to determine the trial KSP, we start by writing the solubility equilibrium equation for lead-2 bromide, PbBr2. We use this to write the KSP expression for PbBr2.
Now, question. My concentration of lead is 0.00125. My concentration of bromide is 0.04125. Do I want to multiply the concentration of bromide by 2? Chat amongst yourselves, have a discussion.
Sure. Oh, yeah.
Before we plug this concentration into the KSP, do we need to double it?
Yes.
So if I tell you that the concentration of bromide is 0.04125 molar, is it true then that the concentration of, true or false, concentration of bromide is 0.08250 molar? Is that a true statement? No. So do you want to double it? No. I bring this up because so often people want to double it because they see the 2 in the PBBR2, you know, you got that 2 there and they want to double it. But if you have found the concentration, leave it alone. You have the concentration. You don't need to do anything with it. Yeah? You only double it if I gave you, like, let's say I gave you concentration of, I don't know, CaBr2. And I said that is 0.2 molar. I would double this concentration to find the bromide. Yes, because this is not the concentration of bromide, this is the concentration of calcium bromide. Yes? So I would only double it if I'm changing from one thing to another. But if I've got bromide, I don't want to double bromide because that doesn't make no sense. Yes? So do not double things if you already have the concentration. Okay?
Here. Because we're using concentrations of Pb2 plus and Br minus, which are added to a new mixture, but are not at equilibrium, we call this a trial KSP.
Or a Q.
We substitute 0.00125 for the concentration of Pb2 plus in the trial KSP expression. And we substitute 0.04125 for the concentration of Br minus in the trial KSP expression here, remembering that the concentration of Br minus is squared in this expression. So to calculate the trial KSP, we take 0.00125 and multiply it by 0.04125 squared, and we get 2.1 times 10 to the negative 6.
Now, what would we do with our trial KSP in order to figure out if a precipitate forms or not? We need to compare it with KSP. Where would you find KSP? In your data booklet on page 5. Page 5. Take a look at page 5. See if you can find lead bromide. So it's 6.6 times 10 to the negative 6. So what can we say about this? Is this too big or too small?
Too small.
Too small. So do we have enough ions to make a precipitate or not enough ions to make a precipitate? Not enough to make a precipitate. So if Ktrial is less than KSP, there's no precipitate.
For the value of trial KSP. Looking on the KSP table, we see that the actual KSP of lead 2 bromide, PbBr2, is 6.6 times 10 to the negative sixth. Comparing the trial KSP, 2.1 times 10 to the negative sixth, with the actual KSP, which is 6.6 times 10 to the negative sixth, we see that the trial KSP is less than the actual KSP. So when the two original solutions are mixed, a precipitate will not form in this case.
And that's it for this. Now, hopefully that gives you enough that you will be able to do the homework, which is to work through a couple of the examples. The examples are in the filled in part of the key where it says filled in. So you will want to do, where is it? Come here. There we go. Nope. Where are you? There we are. Your homework is pages 64 and 65, examples 1 and 2. That's the trial KSP. And then page 59, number 1 and 4. If you want to do more of those, if you feel like you'd like a little extra practice, feel free. But that will at least get you started reviewing what we learned today, both different types. Okay? Okay.
Yeah, I get that.
Right? And I have to rush over to the school board office to pick up the workbooks because they finally have a printer. So I have to run there and then I have to run to the gym. School board is on Canada Way and Guildford.
Oh.
So I gotta go over there. So that's why I am all packed up and ready to go because I gotta be back in Coquitlam by 4:45. But it should be no problem. It's lots of time. Yes,
And also, can you stay at the classroom?
of course. I'll just lock the door and you can close it when you're done. Yep.
I'm not hearing.